A car crash is governed by a specific set of physical laws. Once two heavy objects are set on a collision course, the resulting kinetic energy transfer is inevitable and must be managed. For most of the 20th century, the engineering solution was passive safety. This strategy focused on designing mechanical structures that could absorb the shockwave of a crash and route that energy into the vehicle's frame rather than the occupants. This led to the development of crumple zones, sections of the vehicle designed to crush upon impact. By folding inward, the metal absorbs the brunt of the force, allowing the rigid safety cells surrounding the cabin to remain intact. Inside the cabin, secondary mechanical restraints like seatbelts were bolted directly to the frame. These systems used heavy nylon webbing and metal buckles to physically secure passengers against the inertia of a sudden stop. These mechanical components are entirely reactive. A steel bumper or a safety belt remains dormant until the physics of a crash have already initiated, only functioning once the metal begins to bend. As long as vehicle design relied strictly on physical armor, preventing the accident itself remained an impossible engineering problem. Engineers could mitigate the destruction, but they could not anticipate it. The shift toward active safety changed the priority from surviving a collision to intervening before it occurs. This required the vehicle to monitor its own performance and environment in real time. Consider a scenario where a car hits a flooded section of road. As the tires begin hydroplaning, the vehicle loses mechanical traction, making it impossible for a human driver to maintain steering control. Software interventions respond by calculating friction at each wheel. By rapidly pulsing brakes, the computer regains grip. These systems operate far beyond human capability, pulsing 15 times per second, manipulating physical forces faster than a driver reacts. These micro-adjustments allow the vehicle to counteract environmental hazards as they develop. Safety now relies on a continuous electronic feedback loop that operates far ahead of the mechanical impact. Implementing these early active safety features required adding a discrete electronic control unit, or ECU, for every new function. Each feature, from traction control to lighting, needed its own independent processor. Connecting isolated ECUs created a massive web of copper. Every sensor required a dedicated cable, crowding the interior with heavy wiring bundles. This wiring harness approach eventually reached a physical limit. The weight of the copper increased costs and vehicle mass, while the complexity made automated assembly impossible. To manage this, engineers introduced the Controller Area Network, or CAN bus. This protocol allowed isolated computers to broadcast messages over a shared line, reducing the need for point-to-point wiring. However, even with a shared network, the sheer volume of hardware and copper required a complete architectural redesign. Simply adding more computers to a mechanical frame was no longer sustainable. The solution is a transition to zonal architecture, which eliminates the decentralized wiring harness in favor of a unified digital structure. This design divides the car into quadrants, where local sensors report to nearby nodes, which relay data to a central supercomputer. Safety commands transmit as data packets over a high-speed network, replacing copper cables with digital pathways. Consolidating hardware into a central hub completes the vehicle's transition into a mobile IT network. The mechanical chassis functions as a physical shell for the primary software architecture. This digital architecture allows modern vehicles to fuse data from radar, high-definition cameras, and ultrasonic sensors. This creates a real-time 3D understanding of the road. When the software identifies a stalled vehicle ahead, it calculates the trajectory and closes the brakes before the driver can initiate an action. The intervention happens entirely within the digital network. These modern, stripped-down chassis are designed for automated production. Without the bulk of traditional wiring, precision robotic arms can assemble the frame with high efficiency. Automotive engineering has moved past the goal of building a better steel cage to survive impacts. Predictive processing speed has superseded steel thickness as the primary metric of safety. Protecting the passenger now depends on identifying a threat and initiating an evasive maneuver before physical contact occurs.